we're going to take a deep dive into the world of neutrino detectors.
Right.
These incredible feats of engineering designed to catch particles that barely interact with anything.
Yeah.
But before we get into the how,
Right.
let's talk about what we're actually dealing with here.
Yeah, for sure.
Neutrinos. These tiny, practically massless particles are constantly streaming through us from the sun, supernovae, you name it.
It's true. They're everywhere.
And that's precisely what makes them so fascinating.
Right.
And incredibly difficult to study.
Yeah.
They're like cosmic phantoms passing through us by the trillions each second.
Trillions.
Yeah.
Okay, now I have to ask.
Uh-huh.
How do scientists even begin to detect something like that?
Right.
What makes it so hard to catch a neutrino?
Well, it all boils down to the weak force.
You see, unlike other fundamental forces like electromagnetism, which we experience all the time, the weak force operates on incredibly tiny scales.
Okay.
Imagine trying to high-five a neutrino.
Okay.
Most of the time, your hand would pass right through it.
Whoa.
It's only in those extraordinarily rare instances where you just graze it that you might get a tiny interaction.
Oh, wow.
So
So we're talking about a level of interaction that's almost impossible to imagine.
yeah.
It's no wonder these particles are called ghost particles.
Exactly.
And yet scientists have built these elaborate traps to catch them.
Right.
I'm curious, what are some of the different approaches they've come up with?
You're absolutely right. The detectors are ingenious.
Yeah.
And yes, there are a few main types, each relying on a different principle to capture those fleeting moments when a neutrino actually interacts with something.
Let's start with one that always blows my mind.
Okay.
Water Cherenkov detectors.
Yeah.
These are the ones that involve giant pools of water, right?
Yeah.
Yeah.
Picture a colossal tank filled with ultra-pure water lined with these super sensitive cameras called photomultiplier tubes.
Like Super-Kamiokande in Japan.
Exactly.
I read that it holds 50,000 tons of water.
It's massive.
That's just insane.
Yeah.
But how does water help detect something as elusive as a neutrino?
Here's where it gets really interesting.
Yeah.
When a neutrino interacts with a water molecule, it can sometimes create a charged particle that actually travels faster than light can in water.
Wait, faster than light?
Yeah.
I thought nothing could travel faster than the speed of light.
You're right. Nothing can travel faster than light in a vacuum.
Okay.
But in a medium like water, light slows down a bit. And these charged particles can actually outpace it for a fleeting moment.
Oh.
This creates a shockwave, kind of light boom, if you will, which we call Cherenkov radiation.
So it's like a sonic boom, but with light.
Precisely.
Yeah.
And those photomultiplier tubes I mentioned can detect that faint blue flash, allowing scientists to trace back the path of the neutrino that caused it.
That's so cool.
Pretty ingenious, wouldn't you say?
It really is.
Yeah.
It's like they're using the water to amplify the neutrino's whisper, turning it into a flash we can actually see.
Right.
But hold on, not all neutrino detectors use water, right?
Right.
I've heard about something called scintillation detectors.
Yeah?
What those like?
Scintillation detectors.
Yeah.
These are fascinating, too.
Okay.
Instead of relying on a light boom effect, they use materials that release a tiny burst of light or scintillation when a charged particle from a neutrino interaction passes through them.
Oh, I see.
Imagine it like a microscopic firefly lighting up in response to the neutrino's presence.
So instead of the sonic boom, it's more like a tiny spark.
Yeah, you could say that.
What kinds of materials are we talking about here?
Scientists use a variety of things.
Okay.
Certain crystals, liquids, even plastics.
Wow.
The key is to find materials that scintillate brightly enough for us to detect those faint signals.
The Borexino experiment in Italy, for example, uses incredibly pure liquids to detect neutrinos coming from the sun.
Oh, wow.
They've really taken purity to the extreme in that experiment.
It seems like each type of detector has its own unique way of capturing these incredibly rare interactions.
It does.
Now, what about radiochemical detectors?
Yeah.
Those sound completely different.
They are quite different.
Okay.
These detectors actually use a chemical reaction to capture neutrinos.
Interesting.
It's a slower process, but remarkably effective for certain types of neutrinos. Slow and steady wins the race, as they say.
Yeah, in this case it does.
Are there any particular examples that come to mind?
The homestake experiment is a great example.
Okay.
It used a huge tank of perchloroethylene, essentially cleaning fluid.
Cleaning fluid?
Yeah.
To detect solar neutrinos.
You're kidding?
Nope, not kidding.
Wow, that's wild.
Neutrinos interacting with chlorine atoms in the fluid would convert them into argon atoms.
Okay.
By carefully extracting and counting those argon atoms.
Scientists could actually measure the flux of neutrinos coming from the sun.
That's incredible.
Yeah.
Using cleaning fluid to study the sun.
Right.
It's amazing what scientists can do.
It really is.
And we've got one more type of detector to cover, right?
Yeah.
Solid-state detectors.
That's right.
They sound pretty straightforward, but I'm sure there's more to them than meets the eye.
You're right. There's more to it than meets the eye.
Okay.
They use crystals to detect the tiny recoil when a neutrino bumps into an atom.
So instead of looking for light, these detectors are feeling for a tiny nudge.
Exactly.
That seems even more difficult.
It is incredibly challenging.
Yeah.
Imagine trying to feel the impact of a single grain of sand hitting a wall.
Whoa.
It requires incredibly sensitive equipment and meticulous data analysis.
I bet.
Yeah.
Are there any examples of these detectors that stand out?
One that comes to mind is the Kinesis Plus experiment.
Okay.
They used solid-state detectors to study antineutrinos coming from a nearby nuclear reactor.
Okay, so we've covered a lot of ground here.
We have.
Water scintillation, radiochemical, and solid-state detectors.
Yeah.
All incredible in their own way.
They all are.
But I have to ask. You've painted this amazing picture of these neutrino detectors.
Right.
But why go to all this trouble?
Yeah, that's a great question.
Why are scientists so captivated by these tiny, ghostly particles?
Right.
What's the big deal?
That's a great question, and it brings us to the so what of all this.
Exactly.
Why should you care about neutrinos?
What's the bigger picture here?
Right. Well, for one thing, neutrinos are like cosmic messengers from some of the most extreme and violent places in the universe.
Oh, wow.
They can escape from places where even light can't get out.
Really?
Giving us a unique glimpse into the heart of exploding stars, black holes, and other mind-boggling cosmic events.
So by studying neutrinos, we're not just learning about particles.
Right.
We're learning about the universe's most dramatic moments.
Exactly.
That's incredible.
And it goes beyond astrophysics, too.
Oh. Neutrinos also hold clues about the fundamental laws of physics themselves.
Okay.
Remember how we talked about how neutrinos can actually change flavors as they travel?
Yeah.
This phenomenon called neutrino oscillation shook the foundations of particle physics.
Yeah, it was mind-blowing to realize that these tiny particles could morph from one type to another as they zipped through space.
It completely challenged the standard model of particle physics, which initially predicted neutrinos to be massless.
Right.
Their ability to oscillate implies that they must have at least a tiny amount of mass.
Wow.
This discovery really opened up a whole new realm of questions and possibilities in particle physics.
So these ghost particles are basically forcing us to rethink our understanding of the universe at the most fundamental level.
They really are.
You know, I have to admit, when I first started reading about neutrinos, I thought it was all going to be super theoretical and abstract.
Right.
But now I'm seeing how it connects to these huge cosmic events.
Yeah.
And even the basic building blocks of matter. It's fascinating, isn't it?
It really is.
And to really appreciate the scale of these discoveries,
we
should delve into some specific examples of these remarkable neutrino detectors.
Okay, let's do that.
The past and present.
Let's start with Super-Kamiokande.
Okay.
That giant pool of water in Japan we talked about earlier.
Right.
What exactly has it revealed about neutrinos?
Super-Kamiokande has been absolutely instrumental in several groundbreaking discoveries, confirming that neutrinos oscillate.
Ooh.
This discovery was made by observing neutrinos produced in the atmosphere by cosmic rays, as well as neutrinos coming from the sun. They found that the number of neutrinos they detected was different than what was predicted if neutrinos didn't oscillate.
Oh, I see.
This result basically upended decades of physics.
Wow.
And forced us to revise our understanding of these particles.
So this giant pool of water basically rewrote the textbooks on particle physics.
It really did.
I'm starting to see why scientists are so fascinated by neutrinos.
And beyond confirming neutrino oscillations, Super-Kamiokande has also provided incredible insights into supernovae, those massive star explosions that are some of the most powerful events in the universe.
Oh, wow.
Back in 1987.
Okay.
A supernova occurred in a nearby galaxy, and Super-Kamiokande was able to detect neutrinos that were emitted from the core of that exploding star.
So this detector acted like a time machine, capturing neutrinos from an event that happened millions of years ago.
That's a great way to put it.
Wow.
Those neutrinos provided us with a glimpse into the very heart of a supernova, revealing details about the processes that occur during these cataclysmic events.
It's like Super-Kamiokande is a window into the most extreme events in the universe.
It really is.
Okay, so we've got Super-Kamiokande, this massive detector catching neutrinos from exploding stars.
Right.
What other remarkable detectors should we know about?
Well, let's shift gears a bit and talk about Borexino,
Okay.
the experiment in Italy.
All right, you mentioned earlier that it uses ultra-pure liquids to study neutrinos from the sun.
That's right.
Why is purity so crucial in this case?
It all comes down to reducing background noise.
Okay.
Remember, we're talking about detecting these incredibly faint interactions, and any stray radiation or contamination could easily drown out the signal we're looking for.
Right.
It's like trying to hear a whisper in a crowded room.
So Borexino is like a super clean room for neutrino hunting.
That's a great analogy.
Yeah.
And those efforts to achieve such high purity have really paid off.
Okay.
Borexino has been incredibly successful at detecting neutrinos directly from the sun's core.
Oh, wow.
These neutrinos are produced in the nuclear fusion reactions that power our star. So they carry valuable information about what's happening deep inside the sun.
So thanks to Borexino, we can basically peer into the heart of the sun and study the processes that fuel our very existence.
That's right.
That's incredible.
We've talked about Super-Kamiokande capturing neutrinos from exploding stars, and Borexino looking deep into the sun.
Right.
Are there any other remarkable neutrino detectors that stand out?
I'm sure there are.
There are so many.
Yeah.
But let's move to the South Pole and talk about IceCube.
Okay.
Now, this is where things get truly epic.
Oh, wow.
IceCube isn't just a detector, it's an observatory. A telescope for neutrinos.
Okay.
It's buried deep within the Antarctic ice.
Whoa.
And spans an entire cubic kilometer.
Cubic kilometer of ice?
Yeah.
That's hard to even wrap my head around.
It's massive.
It must take an incredible amount of energy to melt all that ice.
Well...
Or do they even have to melt it?
No, they don't melt the ice.
Okay.
They actually use hot water to drill long, narrow holes deep into the ice.
Okay.
And then they lower strings of optical sensors into these holes. The sensors are spread out over that vast cubic kilometer.
Wow.
Waiting to detect the faint flashes of light produced when high-energy neutrinos from outer space interact with the ice.
So instead of a giant pool, they're using an entire glacier as their detector.
That's one way to think about it.
That's thinking outside the box.
It really is.
But what kinds of neutrinos are they looking for down there, and why go through all that trouble to find them?
IceCube is designed to capture high-energy neutrinos coming from outside our solar system.
Okay.
From sources like active galactic nuclei gamma ray bursts and maybe even the remnants of supernovae.
Wow.
These neutrinos are incredibly rare and carry information about some of the most violent and energetic processes in the universe.
So it's capturing neutrinos that have traveled across vast distances of space, carrying secrets about the universe's most powerful events.
Precisely.
Wow, that's incredible.
These neutrinos provide us with a unique window into the extreme environments where cosmic rays are accelerated to incredible energies. It's like having a cosmic messenger delivering information from the most remote corners of the universe.
That's an amazing way to think about it.
But how can scientists be sure that these neutrinos are actually coming from these distant sources? Yeah.
Space is a pretty big place, after all.
It is.
You're right, it's a challenge, but it's not impossible.
Okay.
When a high-energy neutrino interacts with the ice, it can create a muon, which is a heavier cousin of the electron.
Oh, okay.
This muon travels through the ice at nearly the speed of light. And its path can be reconstructed by IceCube sensors.
Okay.
By analyzing the direction of these muons,
yeah,
scientists can trace the neutrinos back to their sources.
So it's like doing cosmic forensics, tracing these ghostly particles back to their origins across billions of light years.
That's a great analogy.
That's just incredible.
It truly is remarkable.
And in 2017, IceCube achieved something truly groundbreaking.
They did.
They detected a high-energy neutrino that they were able to trace back to a blazar.
Wow.
A type of active galactic nucleus powered by a supermassive black hole.
Yeah.
Billions of light years away.
It's amazing what they're able to do.
So we can actually pinpoint the source of these neutrinos, even if they're coming from billions of light years away. Yes, by combining data from IceCube with observations from other telescopes, scientists were able to triangulate the origin of that neutrino and link it to a specific blazar.
Oh, wow.
It was like solving a giant cosmic puzzle,
Yeah.
connecting a single neutrino to one of the most energetic objects in the known universe.
It's mind-boggling to think that these tiny, almost massless particles can travel for billions of years across the vastness of space and still carry information that we can decipher here on Earth.
It really is.
It highlights the power of human ingenuity and the magic of scientific collaboration.
It truly does.
These discoveries wouldn't be possible without the hard work of thousands of scientists and engineers from all over the world working together to unravel the mysteries of the universe.
Absolutely. It takes a global effort.
It's a beautiful testament to the power of science to unite people in the pursuit of knowledge.
It really is.
It's truly awe-inspiring.
So we've talked about Super-Kamiokande, Oryxino, and now Ice Cube. 3 truly remarkable detectors that have revolutionized our understanding of neutrinos and the universe.
Yeah, they really have.
What ties all of these detectors together?
Right.
What common threads run through these amazing discoveries?
Yeah, it's amazing to see how each detector is like a specialized tool.
Right.
Designed to answer specific questions about these elusive particles.
Exactly.
We've got giant pools catching neutrinos from the sun and supernovae.
Uh-huh.
Ultra-pure detectors peering into the heart of our star.
Right.
And massive ice telescopes capturing high-energy neutrinos from across the universe.
It's incredible the variety of approaches.
Yeah, it really is.
That's a great observation. Each detector is optimized for a particular type of neutrino and a particular set of scientific goals.
Yeah.
Some are designed to detect low-energy neutrinos from the sun,
Okay.
while others are built to capture those incredibly rare high-energy neutrinos coming from distant galaxies.
Right.
It's like having a toolbox filled with different instruments, each one ready to tackle a different aspect of this fascinating field.
And as technology keeps advancing, I imagine we'll see even more sophisticated and sensitive detectors being built.
Definitely.
Opening up even more avenues for exploration and discovery.
Oh, yeah, for sure.
It's exciting to think about what the future holds for neutrino astronomy.
Is.
But before we get too far ahead of ourselves,
Right.
let's take a step back and talk about the challenges of detecting these ghost particles.
Okay.
We've touched on how rarely they interact with matter.
Uh-huh.
But what are some of the other hurdles that scientists have to overcome in this field?
Well, one of the biggest challenges is background noise.
Okay.
Remember, we're trying to detect incredibly faint signals.
Right.
And any interference from other sources of radiation or particles can easily overwhelm the neutrino signal we're looking for.
Oh, I see.
It's like trying to hear a whisper in a crowded room.
So how do scientists make sure they're actually detecting neutrinos
Right.
and not just picking up random interference?
Well, one way is to build detectors deep underground, shielded from cosmic rays and other sources of radiation.
Makes sense.
That's why you'll often find neutrino detectors in mines or tunnels, where they're protected by layers of rock.
So they're like going deep into the earth to get away from all that noise.
Exactly.
But even with all that shielding, there's still background noise to contend with, right?
There is, yeah.
So it's not just about building bigger and better detectors.
Right.
It's also about developing smarter ways to filter out the noise.
Exactly.
And isolate the genuine neutrino signals.
That's where advanced data analysis techniques come in.
Okay.
Scientists use sophisticated algorithms to sift through mountains of data, looking for those telltale signatures of neutrino interactions.
Oh, wow.
And we've seen tremendous progress in this area in recent years.
Really?
Thanks to advances in computing power and machine learning.
So it's a combination of cutting-edge hardware and software that's pushing the boundaries of neutrino detection.
Absolutely.
It's like a high-stakes game of hide and seek.
Yeah, you could say that.
With scientists constantly developing new strategies to outsmart these elusive particles.
And with these technological advances,
Yeah.
we can expect even more remarkable discoveries in the years to come.
It's incredible to see how far we've come in our quest to understand these ghostly particles.
It is.
We've gone from giant pools to telescopes buried in ice, from capturing neutrinos from the sun to tracing them back to blazars billions of light years away.
It's been an amazing journey.
It really is a testament to human curiosity and ingenuity.
It really is.
But I'm curious, what's next for neutrino research?
Yeah.
What mysteries are these particles still holding on to?
Well, one of the most fundamental questions is the nature of neutrino mass.
Right.
We know they have mass,
Right.
but we don't know exactly how much or how they get it.
Right.
Remember how the discovery of neutrino oscillations challenged the standard model of particle physics?
Yeah, it was like these tiny particles were whispering, hey, there's more to the universe than you think.
Exactly. And that's one of the most exciting things about neutrinos.
Right.
They might hold the key to new physics beyond what we currently understand.
So by studying neutrinos, we could potentially revolutionize our understanding of the universe at the most fundamental level.
We could.
That's incredible.
What kind of experiments are being planned to unravel this mystery of neutrino mass?
Yeah. What's next?
There are some really ambitious projects in the works.
Okay.
One that I'm particularly excited about is the Deep Underground Neutrino Experiment, or DNUE for short.
Okay, do you know?
It involves sending a beam of neutrinos from Fermilab near Chicago all the way to a massive detector located deep underground in a former gold mine in South Dakota.
Wow.
A distance of over 800 miles.
800 miles?
Yeah.
That's a serious neutrino road trip.
It is.
But why send them on such a long journey?
By studying how these neutrinos oscillate or change their flavors over that incredible distance, scientists will be able to measure their mass with unprecedented precision. It's like setting up a giant ultra-sensitive scale for these elusive particles.
That's mind-blowing. It seems like every time we think we're getting a handle on neutrinos, they reveal another layer of complexity.
They do.
Are there any other big neutrino mysteries on the horizon?
Oh, absolutely. Another question that's been keeping physicists up at night is whether neutrinos are their own antiparticles.
Wait, their own antiparticles?
Yeah.
Okay, now you're really testing my physics knowledge.
It's definitely a mind-bending concept.
Yeah.
But in the world of particle physics, almost every particle has an antiparticle.
Okay.
A kind of mirror image with the opposite charge. Think of matter and antimatter.
Okay, I vaguely remember that from my physics classes.
Right.
So are you saying that neutrinos might be special?
They might be?
Because they could be both particle and antiparticle at the same time?
Exactly. It's a possibility, and if it turns out to be true, it would have profound implications for our understanding of the universe.
But how would we even know if neutrinos are their own antiparticles?
Right.
What would that look like?
Scientists are looking for a rare type of radioactive decay called neutrinoless double beta decay. This decay process, if observed, would provide strong evidence that neutrinos are indeed their own antiparticles.
Oh, wow.
And to detect this rare decay, they're building incredibly sensitive detectors, shielded from background noise, and capable of monitoring vast quantities of material for years on end.
It's incredible to think that these tiny elusive particles could hold the answers to some of the biggest questions in physics.
It is.
But let's not forget the practical applications of neutrino research, too.
Right.
We talked earlier about how neutrinos could be used to monitor nuclear reactors. What are some other potential real-world applications?
One particularly intriguing idea is using neutrinos to image the Earth's interior.
Oh, wow.
Imagine a giant natural X-ray machine that could reveal the structure and composition of our planet in unprecedented detail.
Wow. How would that even work?
It's based on the fact that neutrinos can pass through matter, including the Earth, relatively unimpeded. By studying how neutrinos are absorbed or deflected as they travel through the planet, we could map out the Earth's core mantle and crust.
So we could potentially uncover hidden geological features.
We could.
Understand plate tectonics in a whole new way.
Yeah.
And maybe even discover new resources.
It's a possibility.
That's amazing.
It's definitely an area with huge potential.
Wow.
And there's even the possibility of using neutrinos for communication.
Really?
Because neutrinos can pass through almost anything.
Right.
They could be used to send messages through the Earth, potentially revolutionizing long-distance communication.
Neutrino-powered internet. Sign me up. But seriously, it's incredible to think about how these tiny particles, once thought to be practically undetectable, could have such a profound impact on our world.
It's a testament to the power of human curiosity and our drive to understand the universe around us. And who knows what other applications we'll discover in the future.
Exactly.
The possibilities are endless.
This deep dive has been an incredible journey.
It has.
We've explored these elusive particles, the amazing detectors built to catch them, and the groundbreaking discoveries they've led to.
It's a fascinating field.
It's clear that neutrino research is a field that's brimming with potential.
It is.
Both in terms of unlocking fundamental secrets of the universe and shaping our future.
I couldn't agree more. It's a field that's constantly evolving, full of surprises and challenges. And it's truly inspiring to see what scientists have accomplished and what they're continuing to explore.
Thank you so much for joining me on this neutrino adventure.
It's been my pleasure.
Your insights have been incredible.
Thanks.
And I'm sure our listeners feeling as inspired as I am.
And to our listener, if there's one thing I hope you take away from this deep dive, it's that neutrinos are much more than just ghost particles. They're messengers from the most extreme environments in the universe. They hold clues about the fundamental laws of physics.
Yeah.
And they have the potential to revolutionize our world in ways we can only begin to imagine.
That's a perfect note to end on. Keep those neutrino whispers in mind, everyone.
Yeah.
They might be fainted, but they have a lot to tell us about the universe and our place within it.